Hello. Today I want to talk to you about reactions of benzene. We talked a little bit about this in class today, but I wanted to go over it in a little more detail, a little bit slower, so that it's clear the sorts of things we're going to focus on. So what we have on the board is just a generic reaction of benzene, where we start with benzene, add a very strong electrophile, and do a substitution reaction on benzene. It's electrophilic aromatic substitution because you start with a strong electrophile, start with an aromatic molecule like benzene, and end up with an aromatic product. The way the mechanism works for this is we form a carbocation intermediate, and many of you have drawn out these sorts of carbocation intermediates in your lab report, where you get this hybrid where the positive charge is delocalized over 3 different positions. And then some sort of base comes in, and the base can be essentially anything that has a lone pair to pull off the proton on the position where the reaction occurred, thus regenerating the benzene ring, right? And then you have a protonated base. And again, that can be something like water if you're running this in acid. It can be Cl minus, anything that has a lone pair. And the key thing for our reactions of benzene is that the reactions differ only in E+, how you generate that E+, and what it is, right? The mechanism for the reaction is identical for all of these. And so what I want to do is talk about the 5 different electrophilic aromatic substitution reactions that we're going to care about, right? And so let's just roll through all of them. So first, halogenation. Halogenation is a very useful reaction, right? And the interesting thing to recognize, and we've seen this before where we've done reactions of alkenes, if we just add X2, Br2, Cl2, whatever to an alkene, we'll get a halogenation reaction to occur. And for benzene, right, there's going to be no reaction if we just do this reaction as written right here. The key thing for us is we need to activate X2, make it even more electrophilic. So the way we do that is add either Fe X2, right, so FeX3, so iron trichloride, iron tribromide, something like that, or Al X3, right? So we add some sort of Lewis acid. That will enable the X2 to become even more reactive, and that will promote the reaction so that we can get a halogenated benzene, all right? And the key thing to think about here is that when we're doing this reaction, what's actually happening is that we're having X2 react with one of the Lewis acids, right? So if, for example, we had Cl2 plus FeCl3, right, what's going to happen is that we're going to have one of the chlorines react with the iron, since it's a Lewis acid's electron pair acceptor, right? And that will generate that intermediate, and this behaves like, so this behaves like Cl plus, right? It's not Cl plus, but it behaves like it, because now what can happen is that benzene can add to the terminal chlorine, and it makes the bond that we need, right? And now we're up into this position where we're doing our electrophilic aromatic substitution reaction, right? So that's part of the mechanism. The important thing about this, the utility, right? The utility that we already know about is we can add magnesium to this, and this is a really useful way to make a Grignard reagent. So you've taken a benzene ring and you've turned it into a really good nucleophile. The other thing we'll see is that, we'll see this in the next unit, is that these sorts of reagents are very useful for palladium catalyzed reactions. All right, so these are the 2 main uses we'll have for these reagents. Make them into a Grignard or in palladium catalyzed reactions. Number 2, it's the reaction that you all know about already, almost all know about, is nitration, right? So for our nitration reaction, as you already know, if you take benzene plus nitric acid with sulfuric acid, you can generate nitrobenzene, right? And just as a reminder, what's going on when we do this reaction, it's important that we remember what the Lewis structure for nitric acid looks like. Right? And when you react that with sulfuric acid, you can protonate then lose water, all right, and there's your electrophile. That's the nitronium ion. All right, and that's what's going to add to the benzene ring when you do this reaction. Okay, uses for these things. One really important use is that you can turn them into anilines. So if you add H2 catalytic palladium on carbon, you turn the NO2 into NH2. These things are very useful for pharmaceutical compounds, right? So these anilines are useful for that. Also useful in dyes, all right? So these are things that we'll use when we do synthesis problems. The other useful thing, and you may have thought about this in the lab, but if you take toluene and you do this reaction and you add 3 nitro groups, that's trinitrotoluene, right? And so that's a synthesis of TNT, right? So a bunch of uses for nitration of aromatics. Right, so let's move on to the third reaction, which is sulfination. Sulfination is the least important of the reactions we're going to see. We'll definitely use the other reactions much more. One interesting thing about sulfination is it's the only one of these reactions that's reversible. So if you have strong acid, you go in the forward direction. If you have dilute acid, you can go in the reverse direction, right? So this is a situation where you can add the sulfonate group and then take it off if you don't want it later on in your synthesis, right? And thinking about the Lewis structure of sulfuric acid, we talked a little bit about this in class today, right? There's sulfuric acid. It can react with itself. And much like what happens with nitric acid, water can leave, thus generating the electrophile, right? And there's the sulfonium ion. And that's the electrophile that you use in the reaction, okay? When we think about these sorts of compounds, these sulfonated benzenes, you know, what are these things useful for? They're useful for sulfa drugs. So in the pharmaceutical industry, they use this sort of chemistry. And the other thing that they're useful for, this is how the industrial synthesis of saccharin works. At least this is one of the steps. So if you look up the structure of saccharin, right, that's the saccharin structure. And this reaction is one of the key steps in that synthesis, right? And again, we're not going to use this reaction as much as the other ones, right? Oh, that was number 3. Sorry about that. Sulfination. Number 4 now is the Friedel-Crafts acylation. Friedel-Crafts acylation is a very important reaction. We're going to use it all the time, right? And when we think about what's going on here, we talked about in class today when we do these alkylation and acylation reactions to form carbon-carbon bonds that our electrophile is going to be a carbocation, right? And when we do our Friedel-Crafts acylation, we're going to use an acid chloride, reacting that with aluminum trichloride. All right, and that's the reaction that we can use to make a ketone on a benzene ring, right? And the great thing about this reaction is there are no limitations for what the structure of R is, right? As long as you can generate the acid chloride, you can do Friedel-Crafts acylation. When we think about what happens in this reaction to form the electrophile, acid chloride plus a Lewis acid, we can have the electrons in the carbon-chlorine bond react with the Lewis acid, and we get AlCl4 minus plus a strange-looking carbocation, right? And that carbocation is actually a resonance-stabilized carbocation, right? You can draw that sort of resonance structure, positive charge on oxygen. This is a relatively stable carbocation because it's resonance stabilized, called an acylium ion. All right, and that's our electrophile in the Friedel-Crafts acylation. All right, so all we have to do is to make that compound. All right, and again, we'll use this quite often, especially since there are no limitations on R. Okay. So the final reaction that we need to talk about is the Friedel-Crafts alkylation. Right, and for the Friedel-Crafts alkylation, in its generic form, we're just going to react some sort of carbocation and put that group onto the benzene ring. All right. So the question is, how do we form the carbocations that we want to use in these reactions? Right. So when we think about it, there are several ways that we can form a carbocation. Right. So if we have an alkene, we've seen that we can react that with sulfuric acid. That forms a carbocation, right? So if we do that in the presence of benzene, we can do a Friedel-Crafts alkylation reaction, right? You could also imagine if you had, instead of an alkene, an alcohol, right? We've seen you can form carbocations from alcohols, right? So a similar idea, can form that carbocation and in the presence of benzene, do the same Friedel-Crafts alkylation reaction, right? So these are two ways that definitely happen, but are not the most common. The most common way would be if we had benzene, react it with some sort of alkyl chloride in the presence of aluminum trichloride, right? In this reaction, we would form our carbocation, right? Just like we did in the Friedel-Crafts acylation, right? AlCl4 minus, right? And then that would react with benzene to give us the compound we want, right? And this is definitely the most common method. An alkyl chloride plus aluminum trichloride, generate the carbocation and go there. And as we saw in class today, it's really important to remember a couple of things about these Friedel-Crafts reactions. For the alkylation reaction, beware of rearrangement. Right? This is a major problem when you're doing Friedel-Crafts alkylation reactions. So don't forget that if you want to do something in which rearrangement can occur, it will occur in these alkylation reactions. Remember, our solution to that is to use acylation and then remove the carbonyl using the Wolff-Kishner reaction, right? That's a useful thing to do. And then the final thing to remember, neither Friedel-Crafts reaction occurs with a metadirector on the benzene ring. So if you're trying to make a polysubstituted benzene ring, if you have a metadirector on the ring, the reaction just doesn't occur, right? And it turns out that these Friedel-Crafts reactions, you need electron-rich aromatics to do those reactions. When you have a metadirector on the ring, it's an electron-poor aromatic because you have an electron withdrawing group, so the reactions simply don't occur, right? So hopefully this gives you a useful overview of the 5 electrophilic aromatic substitution reactions that we're going to study, and that this will help as you continue to learn about these reactions.